Okay. Hi everyone. Welcome to a new scientific moment. Can you hear me? There in the chat. Confirm me if you can hear me. Okay, perfect. So again, hi everyone. Welcome to a new scientific moment. For the new joiners, these are Tenga talks about topics related to our jobs, such as blockchain, crypto, and so on. Of course, we are accepting new talks, so if you have something to talk about, and don't hesitate to reach us through the Open Slack or through the Research and Innovation Forum. Today is talking Ramsés Fernández. He is the lead cryptographer of IOB Labs and works in the Research and Innovation Unit studying privacy-preserving techniques. His interests revolve around homomorphic cryptography, digital signature, and post-quantum cryptography, among other topics. Today, he is talking about hybrid homomorphic cryptography. In this presentation, he will be introducing hybrid homomorphic cryptography, an interesting solution that tries to reduce computational resources while using homomorphic cryptography. The main idea in mind will be to explore its applications in smart contracts. So, welcome, Ramsés. You there?
Oh, hi there. Can you hear me?
I can hear you, but probably it's my fault. There. Can you hear me? Hello.
I can hear you. Great.
Perfect.
So, shall I begin?
Yes, of course.
Great. Well, first of all, thank you for joining us today for a new scientific moments, and above all, thank you for your patience in advance. So, let me share the screen. Okay. Can everybody see this? The presentation, the butterfly? I think so. Let me check. Okay, so the topic I have for you today is hybrid homomorphic encryption. And well, the objective of this presentation will be just a high-level introduction to the topic, to hybrid homomorphic encryption or hybrid homomorphic cryptography, with an idea in mind to explore the potential applications to private or privacy-preserving smart contracts. So the outline of the talk will be the following. I will give you a motivation, and then I will follow with fundamentals. I will present the hybrid framework. Then I will introduce you a couple of words on lattice-based schemes. Then I will go through symmetric schemes, and I will end up this presentation talking about the potential applications of smart contracts, or to be precise, the work we are doing in IOB with this technique, with smart contracts in mind. So let's begin then. The motivation. The main motivation for hybrid homomorphic encryption is that, well, despite the potential of homomorphic cryptography for, artificial intelligence, machine learning, and so on, the associated complexities and the ciphertext expansion are issues that undermine the prospective applications in some of scenarios. For example, in IoT. So these problems, these issues, led some part of the community to start considering the idea of combining homomorphic cryptography or homomorphic schemes with symmetric schemes, with the idea or with the hypothesis of homomorphic schemes give us the power to run encrypted operations or arithmetics directly on encrypted data. And on the other hand, symmetric schemes are a good option due to the low complexity for instance, and they don't have the problem with ciphertext expansion. So the idea is that if we combine homomorphic schemes with symmetric schemes, what we have is something called a hybrid scheme, a combination of two techniques. So the idea or the objective of this technique of hybrid homomorphic encryption is the reduction of resources, of computational resources of the involved devices. And what we are doing in IOV Labs is to perform applied research around this technique with the idea of exploring its applications in private smart contracts. What we have in mind is that if hybrid homomorphic encryption is good for instance, IoT environments, we can use this advantage or the points of low resources devices to run private smart contracts with restrained resource restrained devices. So the first ingredient of this topic is homomorphic cryptography. I will give you a rough introduction. A homomorphic scheme is composed of 4 algorithms. You have a key generation algorithm that creates the set of keys, the public key, the secret key, and an evaluation key. Both the public and the evaluation keys are public, and the secret key obviously is secret. Then you have an encryption algorithm, which takes a message and a key and returns a ciphertext C. We have the decryption algorithm, taking a ciphertext and a secret key and returning a plaintext M prime. And then we have the evaluation algorithm, which takes a function with the evaluation key and a collection of ciphertexts and outputs another ciphertext called CF. As you can see, I have noted keygen, eng, and so on with an H because we will be combining both homomorphic and symmetric algorithms. And this is just notation to distinguish between the algorithms. Okay. We say that a homomorphic scheme is correct if given a collection of plaintext M1 to MK, the following equality holds. I mean, the probability of the decryption of CF being different from the evaluation of F on the plaintext is negligible. I mean, that means that the probability, once we decrypt the computations, of not getting the same computation on plaintext is almost 0. So let's stop for a while here and forget about the probability function and the negligible function. And what we have is that the decryption of CF must be equal to F of M1 to MK to consider the scheme correct. If you change the decryption and what you do is apply encryption, what you have is that CF must be equal to the encryption of F. Remember that CF can be understood as F of a bunch of encryptions, F of the encryption of M1, M2, M3, MK. And on the other hand, we have the encryption of F of something. This is exactly what means to be homomorphism in linear algebra, for instance. You can replace the operation with the function. So the F of a sum of an addition is the addition of M of F's, for example. Okay. This idea will be useful in the next slides. Okay. We can divide homomorphic schemes in 3 categories. Homomorphic, where the function f is a polynomial of degree 1 or a monomial. This can be understood as we are only allowed to perform just one operations, either a sum, a finite number of sums, or a finite number of products, exponentiations. Then we have leveled homomorphic encryption schemes where the function is a polynomial of finite degree and bounded coefficients. Here we have the power to combine 2 techniques to products with additions. And then we have the fully homomorphic schemes where the function is an arbitrary polynomial. And this is where we are focusing. Okay, we will focus on fully homomorphic schemes. Some examples might be familiar to you. For instance, RSA and El-Gamal are both multiplicatively homomorphic, meaning that they respect the products. And on the other hand, for instance, we have a Pellier scheme, which is additively homomorphic, meaning that it respects the addition. Okay, so since we are focusing on fully homomorphic schemes, it's a requirement to talk about lattice. So we can think of a lattice as an ordered collection of points over an arbitrary over a space of arbitrary dimension, like a plane, for instance. Here we have three examples. The first two lattices are lattices on the plane. The third one is a lattice on a three-dimensional space. Okay. We can derive a series of problems that are known to be computationally complex, like the short integer solution, or the shortest vector problem, the closest vector problem. But we will focus on one special problem and its variations. And I'm talking about the learning with error problem, which is one of the hard problems relying on lattice. Okay. And we will focus on learning with errors and the polynomic version, the learning with errors over rings, or ring learning with errors. Okay, so let us consider a random set of vectors modulo an integer q, and let us consider also a secret vector s modulo q. Q doesn't need to be a prime. It's enough with having q as an integer. And then we have the following linear system. We have A1 times S is somehow B1 modulo Q, A2 times S is more or less B2 modulo Q, and so on. We know that if these equations are equalities, meaning that A1 times S is B1, A2 times S is B2, and so on, the problem is easy to solve with Gaussian methods. But Ode Regev, the one who created learning with errors, realized that the problem becomes computationally hard if we, instead of using equalities, use approximations. Have in mind this, or note that the system on the left is equivalent to the system on the right, meaning that being approximately equal A1 times S to B1 is the same as having an error E1 such that A1 times S plus E1 equals B1, A1 times S plus E2 equals B2, and so on. Okay, this is the main introduction to the problem. Here we can derive from learning with error, we can derive two problems. The search learning with errors, where given the vectors AI and B, you have to find S such that B equals A times S plus E. So I'm giving you the blue components, nothing about the error, and you have to find S to solve the problem. And then we have the decision learning with errors, where, oh, sorry for the Spanish, where given the vectors AI and B, you have to distinguish between either B was formed as a combination of A times S plus E, or if B was taken randomly. That's the meaning of sentence 2. So the individual who's taking the problem needs to distinguish between 1 and 2. And these two problems are the basics for the creation of homomorphic schemes or encryption schemes. Okay, all the cryptographic schemes rely, or most of them rely in one of these two problems. Okay, so it's important to see that learning with errors and relearning with errors are an active focus or an active source of research, both in academia and the industry, for the creation of any kind of cryptographic primitive. For instance, we have the Lindner-Picker solution for the encryption and decryption. We have Kyber and Entru for the encapsulation. We have dilithium or Falcon for digital signatures, Actai proposal for hash functions. We have the proposals BFB and BGB for homomorphic encryption. And we can even find proposals for zero-knowledge proofs, commitment schemes, and so on. Some of you might be familiar with the post-quantum competition run by the NIST, the National Institute of Standards and Technology. And you can recognize, for instance, Kyber, Dilithium, and Falcon as as the 3 finalists of the competition. Okay, so let's talk about lattice-based schemes. And particularly, I will focus on 2 of them, the BFB and the BGB proposals. These are the lattice-based schemes getting most of the attention from academia and industry for homomorphic applications, and in particular for HHE, which is hybrid homomorphic encryptions. Both schemes are fully homomorphic, and both of them rely on the relearning with errors problem. They share some similarities among them. They share the same plaintext space. They generate the keys in a similar way, and they handle additions and products similarly. The main difference between them is found in the encryption process. BFB includes some technical modifications that make it a bit more efficient than the proposal BGB. Okay, so we have one of the ingredients for hybrid homomorphic encryption. We know the basics about the homomorphic part. What I'm going to introduce you now is the hybrid part of the sentence. Okay, in hybrid homomorphic encryption, instead of sending all data homomorphically encrypted, the sender, Abe in this case, encrypts the data with a symmetric scheme together with the homomorphic encryption of the secret key. So this can look risky in the sense that I'm sending you something encrypted with a symmetric method together with the key to open it. But the thing is that you are encrypting the secret key with the homomorphic encryption key. So BART, the good thing is that BART can evaluate homomorphically the message from Abe and perform the computations required. So this is the scheme. Abe creates the keys, the public key, the secret key for the homomorphic scheme, and the secret key for the symmetric scheme, computes the symmetric encryption of MIs, the messages, together with the homomorphic encryption of the secret key, and sends it to BART, who computes the homomorphic encryption of the symmetric encryption of the messages using the public key of the homomorphic scheme. Then he performs the evaluation of the decryption circuit, which means that what he obtains, and we will see it later, is essentially the homomorphic encryption of MI. So he can take off or get rid of the symmetric encryption of MI and focus just on the homomorphic part. He then can evaluate the function over the data and send the results to Abe, who will be able to decrypt the results. I mean, and the part of CHMI equals to HEVAL it's a kind of magic, honestly. I mean, it seems to be witchcraft or voodoo, but here you have somehow a reason of why this formula or this procedure works. And I have to warn you that it's full of abuse of notation. But you have that each eval, you can take SDEC out of HEVAL, and you have SDEC using the homomorphic encryption of the secret key, evaluated on the homomorphic encryption of the symmetric encryption. This is the second row. But the funny thing of homomorphic encryption is that you can reverse homomorphic encryption with the function evaluated, which is in this case is STEC. And what you get is the decryption using the secret key of something encrypted symmetrically. And essentially, STEC cancels CS, and what you get is CH of MI. And that's freaking amazing, honestly, at least to me. Okay, so we have two of the ingredients. We have the homomorphic part. We have somehow understood the hybrid framework. The only thing that remains to be somehow understood is the symmetric schemes. I mean, the thing is that hybrid homomorphic encryption combines dedicated symmetric techniques with homomorphic techniques. I mean, a good question could be, may we use known schemes such as AES instead of creating new ones dedicated just for homomorphic or hybrid homomorphic encryption? Why not? It's a good question. The thing is that the answer is yes, but you can find proposals combining AES with homomorphic encryption using the fact or the hypothesis that many devices are prepared to support AES. It's a standard in symmetric encryption. Nevertheless, this combination increases the computation complexity and makes it unsuitable for many situations. I want you to keep in mind that hybrid homomorphic encryption was born essentially to solve problems in IoT environments. So restricted devices are involved in the picture. You can also find other research proposals suggesting the use of public key encryption with homomorphic encryption. And the hypothesis here is that public key schemes can handle products in a more convenient way than what you can do with symmetric solutions. But the main problem of public key schemes is that they have pretty big problems with ciphertext expansion. So you cannot, or you are not, it's not a good advice to use the usual secret symmetric schemes. And you can either use, you cannot either use the usual public key schemes. So you need, that's why you need to create a symmetric scheme created especially for homomorphic encryption that will be used in the hybrid framework. And one of the solutions that is taking getting all the attention is PASTA. PASTA is a proposal which was designed to be combined especially with BGP and BFP. It aims to reduce the latency and the product complexity of both BGP and BFP. The good thing is that outperforms previous dedicated symmetric schemes like FASTA or RASTA. And the best of all is that you can find it in libraries such as SEAL or HELIP, which are the standard libraries or some of the standard libraries in homomorphic encryption. Okay, so we have all the ingredients. We have the concept of homomorphic encryption. We are focusing on fully homomorphic encryption, and that's what led us to Lattice. Then we introduced the hybrid homomorphic framework, and we talk a little bit about why we need dedicated symmetric schemes. Now it's time to talk about smart contracts. And well, since homomorphic encryption allows the arithmetic manipulation of encrypted data, it opens the door to the creation of privacy-preserving smart contracts. And that's what the main reason that led many companies, not just IOV, to start exploring homomorphic encryption in blockchain. The idea that we have in mind is that using hybrid methods allows you to develop techniques that could be applied in lightweight blockchain, which is a framework involving just restrained devices. Okay? Among the existing proposals, I'll say that we are not the only ones. We have, for instance, Zama, Helix or Sunscreen that are exploring the use of fully homomorphic encryption for blockchain applications. But as far as I know, we are one of the few, if not the only ones, trying to explore hybrid methods to be applied in smart contracts. Okay, so just to end up with this talk, I want to share with you the research roadmap that we have in mind is the detection of improvements in BFV and BGP. We plan to adapt some proposals to hybrid homomorphic encryption. And the next step is try to generalize the results we get. And that's all. Thank you.
Okay, thank you very much, Ramsés. It was a great talk. So let's move to the questions. Is there any questions on the chat? Let me see. There are no so far. Okay, let's wait a few minutes. Not in the chat, not in any other channel. So, okay, I think we can wrap up. Thank you very much, Ramsés.
Thank
Again.
you.
And see you next year with more scientific moments for an excited 2023. So, see you later.